So, first thing I wanted to bring up, welcome back from spring break. Number one. Number two, I did get everybody's grades caught up. So what you have in there now is everything that I have. So please take a look and review it and make sure that I did grade everything that you had, and stuff like that. If you have any questions, just shoot me a Discord. Not a problem. We can have a chat about it. But the big thing I wanted to kind of go over fairly quickly was the midterm. The midterm looked really good. I can't access my grades on Moodle. Okay. I see your chat. I don't know why. I'll take a look after class, okay? Um, does anyone else have a problem seeing your grades on Moodle? If you do, just put it in the chat for me. Um, I know. Ah, man. Okay. I thought I fixed it. I must have broken it by fixing it. Okay, I am so sorry, you guys. I will take a look at that as soon as we're done here today, and I will try to figure out what I've clicked to break it. Um, because that's probably what has happened. Because they were working, then they weren't working, and then I got them working again, and apparently I've broken them again. I am so very, 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 very sorry. Um, when I put the grades in for the midterm, they were pretty much all A's and B's. So I mean, they look really good. Um, again, midterm exam looked, I was very, very happy with the grades. The average was an 81 point something or other. Um, which is a little on the low side, but I was still very happy with it. So hopefully that'll make you feel better. The question that most people had issues with was the last question. I will say that. As far as the like the C++ part, I'm trying to think some of the common mistakes. I apologize. I've got my notes up, so that's what I'm reading from. Um, the C++ looked really good. The biggest group of common issues was A, you made it extremely difficult on yourself, and it should not have been nearly as hard as you made it on yourself. Um, which is a typical issue. And then I think B, there was something about some people were making functions friendly and not having the full understanding of what a friendly function has access to. So I'll just kind of leave it there. Um, let's see, as far as the Lisp, the Lisp were very good. It was mostly issues with parentheses. Some people had missing end parentheses, or there was a group missing, or you had parentheses in the wrong location. So I saw on a lot where in you'd have your initial parentheses and your first word is the keyword, but then you would put the two numerics or whatever it is that you were, say you're adding. Well, you'd put the two numerals in parentheses as well. Well, that doesn't work. Okay. So it has to be keyword and then attribute without parentheses in between it. So that was an issue with Lisp. Um, again, making things harder than it has to be. I wrote that down like twice. Um, the one with the loop for Lisp, the biggest mistake was not giving an initial value to the variable that you were using to increment. Okay, so eventually in there you had like a plus equals 1, but you never actually gave a or set a equal to 0 or anything like that. So it would complain about that because you didn't have an initial value. Um, and then the biggest mistake for that last question, which is the one that most people had the issues with, was um, somehow your signs would get mixed up. So the ones that should be negative were positive, and the ones that should be positive were negative. And there was an issue with using, I think it was EXP for exponential instead of EXPT. So EXP is E to the numeric. So if you send it two numbers, it complains because it says there's too many arguments. What you're looking for, because I believe it was like A raised to the power B. What you need is the EXPT, and then you can send it the two. So those were the big issues. But overall, you guys like killed it. You did really good. I was really happy. So um like I said, that was just a little bit of background on the midterms. Um okay. And I will check that access on grades as soon as we're done here today, and I'll put some info back in Discord or up on Moodle so that you guys know that you can see them. Are there any other questions, comments, issues, concerns from you guys? Okay, don't forget Wednesday is in person. I have the um, room at the end of this presentation, and I will post it in Discord and in Moodle. I will write that down on my list of to-do things. So room number for the speaker for Wednesday. Okay, well, we are starting on a brand new topic for the next couple lectures, and we're going to start digging deeper into data types. So we went through a few different types of programming, and we're going to step back a little bit and look at data types, and then we're going to jump back into another programming paradigm. So we're going to look at the type system, primitive, composites. We're going to look at functions, other types, and we'll get into some final remarks. It's just going to be a few classes. Let me see. I think it's just like 3 or 4 classes that we're doing the data types on. Yeah, just like 3. 2 or 3. So we'll see how it goes. And then after we finish up this one, we have the logic paradigm, and then we're into our pet project presentations, and then we're almost essentially done. So let's go ahead and get started with our data type discussion. So data types are essential to any program, and every programming language has a data type or some type of data typing. As we saw in our Lisp, everything was an atom. And then if you look at something that's more OOP, you can break, your data types down even to like more primitive, where it's a double, a numeric, a character, things like that. Even languages that are not heavily typed, such as assembly, if you're familiar with that, actually do support some type of data typing. And a lot of it is due to the fact that we want to introduce how much memory we want, what it dictates format, it dictates a lot of different things. So even though we've got some of those less, rigid programming languages, for the most part, they still actually do have some type of data typing. So this is a challenge, and we're going to get to the answer by the end. But here, declare the variable A and manipulate it before this if statement. Your goal is to make this Java code print yes. Okay. So we're going to figure out how to do this later on. But here I've got an if A equals A, system.out print line no, otherwise print yes. Our goal here is to actually get it to print yes. So we want to manipulate A for this to happen. What is a type? Well, when we declare any kind of variable as a specific data type, we are stating that the values for that variable are going to belong to that type set. And that type set is going to be defining its characteristics and how we use it and what we use it for. And it defines that set of values and the possible operations and what that looks like, okay, on those values. There is a lower level representation, but we're not going to go that deep into it. We're going to kind of stay more on the high level. But what I mean about defining the possible operations, so for example, if I use the plus sign, if I use it on a numeric, it's going to add those numbers together. 2 plus 3 equals, and you're going to get a result. Whereas on the other hand, I could possibly use it for a string, and it actually concatenates two strings together in some languages, right? So even though it's one operator, it technically does two different things. It concatenates based on data type, or it actually does an arithmetic function. It's not possible to cover every single possible data type for all programming languages, but what I want to do is introduce you to some of the more basic and more universally known data types. And we're going to show the connection to mathematics if and when we can and what that looks like. Okay, so we're going to explore as many as we can within a given time frame. Data types can be divided into two big main categories. We have what we call traditionally a primitive type or a composite, compound, complex type. Okay. The primitive type are those basic types for the language. So, for example, integers, character, Boolean, real numbers, things like that, things that cannot be broken down into any smaller of a unit. Okay. Now the compositive, compound, complex types, it's going to be everything else. Okay. Technically, a string is considered a compound type because it is a group of characters. The character is the primitive type. Okay. But we can also look at unions, records, structures, things like that. Okay. All of those are considered that compositive, compound, complex type. Usually I say compound, but just so that you know, kind of those three words all really do mean the same thing, not primitive. The type system in a given programming language is going to define how we handle each one of those data types. Okay. And typically it's in two areas. We do type checking and then type safety. So type checking is going to verify that what you're doing is compatible to that type. Okay. And then safety is the errors. Okay. So when you're doing type checking, your language is going to verify what you're doing is able to be done. Okay. And this can be done either statically or dynamically typed. Safety, on the other hand, is going to be what is valid and what is invalid. And we can say that it's either strongly or weakly typed. Okay. So checking is static, dynamic, safety, strong or weak. Okay. There are a few languages out there that are untyped because they really don't have anything. It's just generic. Okay, so just generic storage kind of. So some assembly, and some of the other really obscure ones don't really have a type system when it comes to the data that it has. It just kind of has chunks of memory where you just throw in stuff. Okay, so makes it a little bit harder to learn, and a little bit harder to organize. In type checking, we've got the static. We talked about static and dynamic. So static is most of that checking is done during compile time, and therefore you have to explicitly tell the code what type you're going to be given, say, this variable. So this is usually where we are when we're looking at Java, C, C++, things like that. Okay, where you're going to say, I've got a variable, it is a double, my variable name is X, and I'm going to give it a value. Okay, you're telling it that it's going to be a double because that's being done at compile time. On the other hand, dynamic means it's done at runtime. And in dynamically checked languages, you don't need to explicitly tell the code what that variable is, it could possibly change. So if you've worked in, say, JavaScript, or some of these other ones listed here, for JavaScript, you can have a variable in which you treat it as a double, and then a few lines later, you treat it as a string. And it kind of does it on the fly and it does it for itself. So that is the main difference between the statically and then dynamically typed. The dynamically typed will more than likely be kind of shorter code, but again, it's a little bit harder to keep track of those things, and keep yourself organized. Now, safety, strong and weak kind of makes sense. So a strongly typed has stricter rules. A weaker type has fewer rules in checking. So for a strongly typed, we've got Java, Ruby, Smalltalk. This implies that errors and exceptions are more likely to happen during the compilation part versus the runtime. Okay. Now, weak or loosely typed have few rules and it will throw less errors during your compilation, but you may find yourself with a bunch of errors or not acting the way you think it should during runtime. So for example, C and JavaScript. JavaScript to me is kind of notorious for this because you've got that dynamically type plus weak safety. And so you're, like I said before, you're able to basically transform a variable from any primitive type that you want into any other primitive type. So as it compiles, it doesn't know which one you're talking about. So it just kind of says, okay, whatever you want. But during runtime, that is when it will try to start and use that variable. And if it's not the type it thinks it is, it gets a little confused and you get more errors. So strong and weak, they have their pros and cons on each, right? Strongly, again, remember compilation is with strong, weak is more runtime errors. There are other type system classifications when we're talking at, just the type as a whole, such as explicit declaration of variable types, manifest versus inferred. So manifest means it's explicit, inferred, kind of as the word implies, it's not explicit. We have equivalency of types and subtypes, nominal and structural. There are so many out there. There's abstract, dependent, intersection. There's a whole list of them. But what we are going to talk about is we're going to talk about those more common classifications of the strong and weak and the dynamic versus static. Okay, so just know that there are other type systems out there, but that's going to be beyond what we're going to discuss here. Oh, that slide looks terrible, doesn't it? Sorry about that. So, warning, type system classifications. The type system classifications are not going to be exact because it is based on whatever language you're looking at. Okay, so if we're looking at overall, every language has different options and features in order to use that type. So, for example, even though Java is considered a statically typed, we can kind of manipulate it to use the dynamic typing, which is in the newer versions of Java. Okay, so we've got that var command with giving it a variable name and then doing some new stuff. And that way, we are implementing the dynamic type system. But it's better to think of these as guidelines for your most common case. Okay. This is not strict definition. And this kind of goes back into when we were looking at those paradigms, right? Some programming languages fall into multiple, some lean more towards one than the other. Some are possible to implement multiple, but one is kind of its more natural state. What we're looking at when we talk about these type classification systems is its most natural state, probably more true to its origins, what we're used to doing, right? This was something that came along in Java later on when they found a need for doing dynamic typing. It was not really truly invented. Java was not invented in order to do it this way. Okay, it was kind of something implemented after the fact. Let's go back to our primitive data type. So primitive is going to be your simplest data type in any programming languages. They are going to be atomic and they cannot be decomposed into anything smaller. So by using primitive types, we can build then more complex data types. Okay. So in programming language, each programming language is going to define its set of primitives. Some languages are going to be stricter or have stricter definitions than others. Java, remember, we're talking it's a strict, has an exact definition of the size of its primitives. Okay. And when you go back, when you learn Java, you probably learned a double holds this many. A unsigned int is this many, right? Not all languages are that restrictive. And it can go based on the environment, the operating system. But for most, and the compiler, but for most things, there is kind of a general rule of thumb for what they look at, what they use for their primitives. Okay. Like I said, Java is a really good example for strict because you can look up and say, how much memory am I going to use if I use an int? And it is explicit out there. Not so much in some of the other strict languages, but again, it's there's so many variables at work here, right? What kind of resources do you have? What are you using to program? Things like that. How open is the primitive type to be defined by the compiler or environment? Okay, how many bits or bytes does an int have in C and C++? How many bits, bytes does an int have in Java? Okay, some of these we know the answers to much easier than others. Okay, if needed, are we able to find the boundaries of the primitive? Okay, a lot of these are published. A lot of these numbers we've learned, right? It goes up to a negative something to a positive something. Okay. Another big thing is what operations are supported by a primitive. Can I round? What exceptions does it have? Can I do conversions, etc.? Okay. So what happens in C or C++ if we go over or under those bounds that I'm talking about? Okay. How does it handle that? Okay. These are some issues that kind of arise when we talk about primitives. Now, an integer is going to represent a specific interval in the integer set. So usually programming languages are going to offer different types of integers in varying sizes. So sometimes there's an int, an unsigned int, a long int, okay? It's all that's doing is giving you more memory space for that data type, okay? Some integers actually do suffer from environment or compiler. So for example, C, an int can have 16 bits in some operating systems, or if you have a 16-bit hardware, or it can have 32 bits if you're running on a 32-bit hardware system. Okay. So that in that case, it is based on what your hardware's basic unit is, not necessarily that of the programming language itself. In C++, we've got char is actually an integer, a short, int, long, and a long. Okay. So by default, we've got 1 bit, the leftmost, is used to control if it's negative or positive, because remember, integers can be either one. And then we can expand the number range that we use. If we say it's unsigned, by reclaiming that bit, because we're going to say it's always positive. So we can take that bit back. So that's how it uses the space allocated to its benefit. Okay. Depending upon your environment or your compiler, your short, your int, and your long can have all different sizes. Okay. The major restriction that C and C++ has is that each type cannot be smaller than its predecessor. Okay, so in C and C++, as you look at ints, the amount of bits and bytes used is going to increase and it will never decrease. Okay, so that's the order it kind of puts it in. Here, for example, I've got my char, short, int, long, and long, long. So these numbers for the number of bits, it's kind of like a minimum. So you can see here I've got some question marks, especially for short and int. Those questions, it's going to be based on hardware at that point. Okay. So let's look at the int. If you're just going to be 16 or to something, whatever you have, whatever you're using. And it's going to be your minus 32,000 to plus 32,000. Okay. Your short and your int are going to be the same. But then if I want to do a long, I'm going to add another bit in there, which is going to put me up exponentially on my numbers. Now, if I were to say an unsigned int, what it does is because I cannot have negative, it's going to take away that negative. So I'm going to start at 0 and go all the way up to a positive number until I run out of bits. Okay, so it's really looking at that bit memory space. You can use the function size of, and it will return the size in bytes of the type. So if you want to see what your processor or your hardware allows, you can use that size of. There's also some built-in constants, int max, int min, short max, short min. There's a few of those, and that will actually give you the range value of what the smallest integer can be, what the largest, same thing with short, long, things like that. So if you're ever curious to see what your processor is doing, especially in C and C++, where it is dependent on compiler and hardware and what you have available, you do have the ability to go and look. In Java, on the other hand, remember, Java is much more strict and it has a very strict and precise definition for its integers. If you look at this table, there is no variations. A byte is 8 bits, a char is 16, a short is 16, an int is 32, and a long is 64. No ifs, ands, or buts. Okay. All these types are signed except for the character, which is unsigned. Okay. And we don't have the possibility to manipulate that bit the way that we do in C to give me more space. Okay. Java, just like C and C++, they do have some classes that are going to be available to for every single primitive type. So you've got max value, min, and value. But what you have to do is you have to put that class in front of it. So integer dot max value into or long dot min value. And you can get that same group of data out. And you'll notice, though, for Java, those numbers will not change no matter where you're compiling it, whether you're compiling it on a different operating system, regardless of your hardware. These values, when you do it through Java, are always, always, always going to be the same. Okay, so that is a real big difference between those two. Now, integers in Solidity. Solidity is a language to code smart contracts in Ethereum. So every computation and data storage or manipulation is charged in Ethereum. Therefore, we need to be really particular with how many bits we use in every single variable and every single function. Okay. Therefore, our language is going to be much more restrictive with what we're allowed to use because we have to account for every single bit. So we can use either unsigned or signed, and then increments of 8, okay, up to 256. So for example, if we say unit 8 is going to represent an 8-bit unsigned integer. Okay. And then int 32 represents a 32-bit integer. Okay. So in a language such as Solidity, in order to define an integer, you as the programmer get to choose how many bits are being used for that variable. So in Java, I had that set grouping. In C, it was a little bit more willy-nilly. In Solidity, I'm going to tell you I want 8 bits. So I'm never going to exceed this value. I want this many bits up to 256. Okay. You can see how all three languages really deal with integers in completely different ways. Okay. So now characters. In most languages, characters are just a type of integer followed by some method of transferring that integer into an actual character. Okay. C and C++ use the ASCII table. Java uses Unicode. Okay. So C and C++ uses the 8-bit ASCII table. Java uses the 16-bit Unicode. There are some languages where characters are not considered integers. So like we did in Lisp, Pascal does not as well. But most of the languages that are kind of the most current do consider it an integer with some sort of conversion already built in to transfer that integer into some sort of character. So in languages where characters are in fact integers, we can treat them interchangeably. Okay. If it is a strong typed, such as Java, we may have to cast that into what we want it to be. But here in C and C++, I can say character A, or I'm sorry, character variable named C equals the A plus 2. And then I can actually have an integer D saying that it equals C plus 1. And in this case, it's going to treat C as if it were the integer and not the character representation of A, let's see, B, C, right? To have the integer ASCII value in Lisp, Pascal, one of those other ones where it's not treated as an integer, you do need to call some type of function to do that translation for you. Most of the time, these functions are already built in. So in Lisp, for example, which is the one that we just did, we've got character to int. Okay, that is a keyword. It is something that it knows what to do. It is a function call, and we're sending it A. Okay, and so Lisp, if I want to transfer a character into an integer, I'm able to. It's just not automatic as it is in C and C++, or it's not as easy as in Java where you do like a typecast. Booleans in every language, you've got two values, true or false. Fun fact, your AGOL 60 was the first language to actually have a Boolean type, and it's most often used in logic comparisons, and we can use it to add extra security. The reason why a Boolean was invented is that it really only needs a 1 bit, okay? It's a yes or a no. It is a 0 or a 1. That's all you get for a Boolean. And therefore it reduced the amount of memory that was being used for sometimes these larger variables, and it conserved memory by only using 1 bit. Now, that being said, most languages do use a full byte for a Boolean, just to be consistent with keeping it in those byte groups. But technically, you only need a single bit. In C and C++, there really isn't anything that's technically a Boolean, okay? Most of what we program, a 0 is going to be false and anything else is going to be true, okay? There is a bool, B-O-O-L, type, but it's an integer, okay? So technically, it doesn't hold that true and false. Any comparison is going to return an integer, and then we can use the integers and the bools interchangeably in C and C++. But for the most part, a 0 is false, and then anything else is going to be true. It is useful, but most oftentimes it's kind of confusing. Okay. So that's kind of the main reason why the newer languages such as Java and C# actually have what are considered proper Booleans. So when I say true, it means something. When I say false, it means something. Okay. So for example, code number 1, I and J are both equal to 0. If I equals 1, J equals 10, print F, blah, 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 blah. Okay. I can look at, oh, sorry about that. I can, if I look at the first one, if I use those zeros as being falses, right? So if I is false, J is false. If I equals 1, J equals 10. If I is true, then J is true. Okay. So I can do it in that way. If I actually, code 1, 2, and 3 here are all the same. So if you look at code 2, if I can actually leave them as numerics. So the big difference here is the I equals 1. Okay, so I've got the double equals at the top, which is the comparison. I've got the equals in code 2, which is the assignment. And then in code 3, I've got the plus equals. Okay, so but everything else is the same. 2, if I'm able to change it between true and false by just adding a number to it or setting it equal to a different number. So if I assigns true, then J is 10. Okay. This is where it starts getting a little confusing and you're increasing bugs when you're dealing with Booleans in C and C++, because technically I'm treating it as a Boolean, but at the same time, it really is an integer. Okay. So I'm not able to say if true or if I. Okay. In Java, you can do things like that. Makes it a little bit easier to follow as you go through. Real number. So a real stores some type of real number. Your precision is going to vary from language to language. And just like we did with the integers, there are some languages, once again, that allow you to define your precision. But for the most part, your precision is based on how many number locations you have available and things like that. So a float is an IEEE standard for real types, float, and double, which many, many, many languages have adopted. C, C++, C#, Java, a lot of them. Okay. There are some issues with this floating point representation. Therefore, we do have an alternative as a fixed point. Okay. And a fixed point real type is an alternative to that floating point. So floating point real types, a floating point changes the representation of your number to fit into a significant digit 10 to the something. Okay. And it makes it a little more complicated. Okay. But it's only going to store a specific amount of numbers when it's put into that type of formula. So for example, a 32-bit float, there's 1 bit for your sign. So you take 1 off for that plus or minus. You've got 8 bits for the exponent and 32 bits for the significant. Okay, which is the number of significant digits. Okay. The difference between the float and the double is a 64 as opposed to a 32. You've got that same 1 bit, except you've got 11 for the exponent and 52 for your significant. Okay. So floating points are based on exponent, always. Okay. So it's not going to save it as 3.14. It's going to save it as 0.314. 314, 10 to something. Anything that exceeds those boundaries of those bits that we have are going to be rounded. Okay. If you remember the factorial example for Java, it rounded the result for 100 factorial. The binary representation may also cause some imprecision on your float value. So for example, 1/10 equals 0.1, print 1/10. I can also print 1/10 to 25 decimal places. Okay. Sometimes you'll get 0.1000000. Okay. Have you ever done it and you've gotten like 0.900009 something, and but when you round it, it comes to 0.1? That's when it can start getting a little frustrating for you. At least it was always frustrating for me. There are special values when we look at floating points, and these are standard ones, so not a number, plus infinity, minus infinity. These are going to be our exceptions to the rules for those floats. Okay. So NaN is not a number. So if I attempt to create a number that does not exist, so here for my example, I try to do 0 divided by 0. That doesn't exist in mathematics. Okay, therefore, my output is going to be not a number. I am also allowed to create something that represents positive infinity and then something that represents negative infinity. And again, this is a Java example. So 1/0 and then a -1/0. Okay, you can't divide by 0 because it goes to infinity, if you remember your graphs in mathematics, but it will have a kind of a character representation of what that is by saying plus infinity or minus infinity. But it is representing that floating point. Now, the not a number is undefined in mathematics. So anything that's going to generate a complex number in some languages, we found out Lisp actually likes complex numbers. A lot of programming languages, if it gets to a complex number, it will actually generate a not a number. Operations with something that already has a value of not a number. And again, those undefined mathematical operations. Okay, so 0 divided by 0, infinity over infinity, 0 times infinity, things that don't really exist. Fun fact though, not a number is always going to be equal to false, which is a little weird to think about, but it is something that can be used to your advantage. If you are trying to do some kind of mathematical computation. Fixed point real types, remember, this is our alternate to the floating point. So a fixed point have one part of the storage created for the integer and another part for the decimal. So this is a little different. Remember, we had the exponent and the significant prior. This, we've got the whole number and then the decimal number. So for example, 12.3 is going to be 12 is stored in the integer part, and the 3 is in the decimal part. And then it knows to format it as a 12.3. Okay. Solidity, that one that we were talking about before, has a type fixed n times m where there are multipliers. But we could actually implement some kind of we can also implement some kind of programmer defined class where it holds two variables and one is the whole number and one is the decimal. That would be kind of cool, right? But anyway, in Solidity, if you create a fixed 16 times 8, it's going to create a fixed point real number with 16 bits for the integer and 8 bits for the decimal. So again, remember, Solidity is very particular about saving space, using only what you need. It doesn't give you anything extra. So you are also able to define your fixed points in the same manner. In complex numbers, there are a few languages that they really are few and far between that will support a complex number as a primitive. Okay. Some of them do have them as compound or complex types, but some, like Lisp, which we saw, actually has it as a primitive. Python has a complex type, but it is considered a class and not primitive. And there is no complex primitive at all that is built into C, C++, C sharp, and anything that turns into a complex number. So if you try to take the square root of a negative number, it'll automatically default to a not a number. Okay, it doesn't even try. It's just like, nope, doesn't exist, and it kind of goes off. Um, a lot of mathematical functions either need to test for um, complex numbers or the ability to actually manipulate complex numbers. And that's where Lisp actually does kind of come in handy. So if you're here, example, square root of -4, it's going to give you 0 and 2. Okay, so it's telling you 0 is your number and then 2 is your imaginary part. I don't like complex numbers. I never did like complex numbers, like in math. Okay, so that is all of the stuff we are going to cover today for the data types. So we went into all the primitive stuff with the integers, the reals, and we're going to go a little bit more into some of the compound and complex. We'll start that next Monday. So here is our list of what we are currently doing. So assignment 2 is due Wednesday, 3 is next Wednesday. And now I'm going to start putting our pet project information in there because we are now in March and the projects are going to be coming up faster than I would like to admit, even myself. So the actual written project is due Wednesday, March 27th for all the groups. And then presentations will start Wednesday, April 3rd. So seems like it's far away, but it is going to creep up on us very, very quickly. Wednesday, we will not be meeting online at all whatsoever. And you will be asked, if possible, to attend a speaker in KH309. And hopefully you know where that is because I don't, because I'm not there. But we have a really interesting speaker that is coming. So I hope I'll try and get his bio and put that in Discord as well. We'll put that on my to-do list also. So that you guys can get a little bit of background information before that class on a Wednesday. So, we do not have any more homeworks. The homeworks are done from here on out. It's just those assignments. We do not have any assignments for this section on the data typing. We've got assignment 2 and 3, which you guys have already been able to do. And there's one more for when we start Prolog and the logic paradigm. And that's really it for the grades as far as class goes. I will be checking in Moodle as soon as we get done here to see what in the world I have done in order to break Moodle. Nope, wrong words. Are there any questions, comments, concerns, anything like that? No? Okay. Sounds good. So I will see you guys back online next Monday. And again, be there in person on Wednesday at KH309. I will put it in Discord. I'll put it in Moodle so that everyone doesn't forget. I do see a homework 5. Ooh, I don't know. I'll take a look. I did have a homework 5, but I thought I got rid of it. So that's on me. Yeah. And I got rid of it because everyone, usually by that time, everyone is so like elbow deep in pet project stuff and presentations and everything else. Like it was just kind of a hot mess express. But let me see what I got. I'll take a look at it. Okay, my friends. I will see you on Monday. Have a great time with the speaker. I'm gonna post his info. I'm gonna try and fix the grades. I'm gonna put the room number, and I'm gonna check on homework 5. That's my to-do list for today. Okay, awesome. Sounds like a plan. I will see you guys next week.
Thank
Bye.
you. Bye. Thank you.
Thank you.